In our second lecture this morning, João Pedro dos Santos from the University of Montpellier will speak about distributions with locally free tangent sheaf.
Thank you very much. So I thank all the organizers, especially Jorge, for this opportunity to talk here. And I wish Fernando a very happy birthday and many more years to produce beautiful mathematics just like the one which motivates the following work. And so this is joint work on with Jorge. And let me start with the introduction. So I take the following space, okay, so P and C. So I'm working over the complex numbers now. And I look at the space of forms, which is, let me make a huge parenthesis here. So omega is a form of some certain degree, and so a Q form on Pn. And and I throw in some conditions for that, and I want it to be a singularity, so maybe like that. It's simpler. The codimension of this locus is at least 2. And I want it to be decomposable, so generically decomposable. So this is usually called LDS. And well, of course, you can throw in integrable if you want. But and well, since you want to do some remove redundancies, so you just divide by the action of scalar multiplication. Okay, so from what I understand, then it's an important observation of Ayrton Medeiros is that once you define this guy, every time you take a omega in this space, then you associate to it the following sheaf, which is the kernel of omega, in which you define just like you define the kernel of a quadratic form in your favorite bilinear algebra course. It's just V, which is tangent to Pn, and then omega V, and whatever you plug in makes it 0. So this is a subsheaf of Tpn, and this thing here gives you bijection between this guy and, so let me say like that. Saturated and didn't leave out. So of T. So, and this thing here is bijective. So let me say it like that. Okay. So now once you've described the space of forms, and you have one side forms and the other you have sheaves, you can always say, if I vary a little bit the form, how will the sheaf vary a little bit? And then the question, which is quite interesting, sorry. So is this thing continuous? In some sense, I mean. And the theorem which I state here, and it's due to Jorge and Fernando, so is as follows. Suppose codimension of omega is at least 3. And the bundle which you are working with is a sum of line bundles. Then this remains true in the neighborhood. In the neighborhood. For all. Okay, so now we want to expand a little bit on this result. So my goal, the rest of the talk, will be to expand on this. So of course, here there are other conditions. You see that there's no integrability here. Okay, so you can throw in integrability and then you have other results. But let me concentrate on this simpler form. Okay, so let me give you a setup. Is as follows. I take just to give you a name. Right? I work like that. Smooth of Noetherian. So I only have smooth morphisms between a Noetherian scheme. And one time I did that, I give myself a working definition just to have a common language to talk to you all, which is a definition. Let me call it relative distribution. Relative distribution on X over S is just a T. So let me call it a distribution V. Is a subsheaf of the relative tangent sheaf. And since I want to be economic, I'll try to write a T of F. Okay, so F is my morphism from X to S, and X over S is T of F. Okay, and so this is a subsheaf, and then I need something else, and I decree that the normal bundle, which is by definition here, just TF over TV. Okay. So apparently there are two schools of thought in foliation theory. One which likes to call this guy the normal bundle, the other which doesn't like to call this guy a normal bundle and has to dualize this thing twice. Okay, so, but I follow the later, but for the talk I'll use the former. So this guy here embeds into NV double joule. And so let me just remark. So this is a distribution. So this is extremely weak, okay? Because I don't want to assume anything about S. So S can be as singular as it gets, okay? So non-reduced, whatever it is. And this thing here is just my definition, so I remark that this is in commutative algebra, a sheaf that does that means, now M is torsionless. So that's the name they give to that.
Do you want this to keep projective when you stick to the fibers?
Not at all. And yeah, so this is answer to Eduardo's question, I suppose. No S flatness. So I don't want S flatness. Okay. Result. So here's the theorem. F proper. And I consider the following condition, which is just like the Kodim condition. Oh, so sorry, forgot something. So there's something here missing, which I forgot. Just for the sake, well, people know what it is, but I will define it anyways for everyone. So a definition which comes in with that is I define the singularities of V as being those X and X such that N V X not free. Okay, so this is done. And now the theorem F proper. And I assume this thing here. Sorry, which one? This thing here. So I suppose that the singularities are not big. So assume. Conclusion. The locus where the sheaf is locally free, so now S in S, T V of S, and now it's the moment of anxiety for algebraic geometers. What is TV of S? So I'll get there. Is locally free. Open. So let me just give you some context here. So what is TV of S? It's not TV restricted to the fiber. Okay, so it's TV restricted to the fiber where it should be, where everything is very nice and locally free, and then you spread around. Okay, so so remark. TV of S. So V of S is the foliation or the distribution restricted to the fiber. So it's the tangent sheaf of V of S. And what is V of S? I just define it as the obvious thing. I take the image of T V restricted to S. I send it to T X of S. Saturate. Okay, so this guy is pretty nasty. Okay, so you're doing a lot of operations here. So you're taking an image and you're saturating and so on and so forth. And so this is one of the difficulties. And the second one remark I want to make is this is false. Okay, so this is false, plainly false. Okay. So now I have this theorem, and I will not try to explain too much of the proof, otherwise I wouldn't have proper time. So let me move on to variations of this on this theme, which will allow me to give you something more substantial. And this is as follows. So recall that here I had stuff which is sum of line bundles on projective space. And sum of line bundles in projective space do not deform. Okay? There's no H1. So now it's the same thing. I'll throw in this the condition, and you do a little algebraic geometry, and then you get the following variant of this theorem. Okay? So I take M over K, some field, and I assume that M is smooth. And proper. And K is just some field. And I take the setup as X equals M times S. And here I have the projection, and I have F. So this is my setup. So I'm not deforming the X. Okay, so X stands still. I give myself a vector bundle over M, which is rigid. So rigid is one of those overburdened words in algebraic geometry. So sometimes you have to read the whole paper to figure out what the rigid is. But here I'm going to make life easier. I'm going to say rigid is just, there is no X1. Okay, so it won't deform. And so now I take, let V be a distribution on X over S, such that the codimension condition holds. So here I'm saying V okay, so that it will not meet the fibers in a too big a singularity. Then this set, so does it have a name? No. S and S, such that T V S is equal to E, while E is some base change here, so fill in the blanks, is open. Okay. So, how you can apply this thing? So you can apply this thing very naturally to rational varieties. So because vector bundle, the trivial vector bundle on a rational variety is rigid, and so you can remark. So here, no assumption on the characteristic or anything. M is rational, OR is rigid. And it works also for rationally connected, or at least separably rationally connected. Okay? Oh, very nice. And what else? So I leave you with the slogan if you're somewhat bored by all these things. So the slogan is TV trivial. So this is something for take home, also trivial. Near 0. Okay, so this is the way we like to think of this thing, or at least I like to think of this thing. And why is this interesting? Because foliations are distributions with trivial vector bundle. You can think of them as actions of groups. So it's just saying that if you take an action of a group and you deform something inside of the world of foliations, it's still an action of a group. Okay? Okay. So that said, let me move on to actions. Action for.
Near means in the Zariski sense?
Sorry?
Near in the Zariski
Yeah.
sense?
No, I mean, here K can be FP, right? Actions of groups? No, action foliations, yeah. It's not actions foliations, action foliations. So let me, what I'm doing here, okay, I'm setting up the stage to apply this theorem to something which can give you a concrete example, okay? So what is this? So let me take a field, x over k, smooth and smooth proper, why not? And let me give myself a group G, which acts on the left of X. And from that, I get an infinitesimal action of the Lie algebra of G into H naught of the tangent. And of course, from that, I get a map from G to the tangent bundle himself, which I call it natural. Okay? So this is just the infinitesimal generator of the action. Okay? So of course, when you look at this, there's very little chance of this being injective, so there's very little chance of this giving you a foliation. So what we are going to do, we are going to look at smaller algebras here and see what happens in here. So this is far from injective. Okay, so this is not a good distribution. It's too big. And, so we want find subalgebras H inside of G such that this is a good x sits inside of Tx is a foliation. Foliation, and so it means that it's saturated and codium of the singularities is at least 3. Okay? So as I learned from Jorge, well, usually when you are in codimension 1, you're going to pay, so there's not much hope. Okay, so you have singularities being codimension 2. There's nothing you can do about it, at least in projective spaces. And now, so finding this is not so trivial. And I would like to, what I'm going to do next, I'm going to give you situations where this is satisfied. And I'm going to use these situations where this is satisfied to relate subalgebras to foliations. So the space of subalgebras to the space of foliations. So then use this use theorem to compare S-Lee dimension 2 and fall dimension 2. So I put 2 downstairs means that some normal bundle here. So as far as I can tell from reading the literature, this idea to look at this guy inside here, so this is somewhere in Cerveau Déserti, they have a work. And then there's Jorge and Fernando's paper on the matter, which deals with this sort of theory. And then recently there's Velázquez also, he wrote a paper on that. So you have this other contribution now. So let me move on to give you the examples. So now, examples. So the first one you want to use is Pn, right? So Pn, and at least 4. So recall what I'm doing, I'm looking for subalgebras of the Lie algebra of Pn. So the Lie algebra of Pn, the global tangents are SLn plus 1. And I'm looking for subalgebras where I have this condition here. Okay? And so you do it by hand. So you take J, so it's Jordan block, and you put a bunch of zeros here, 1, 1, 0. And here you fill in with your favorite Jordan form. You take H. So this is, I have to get it right, 4, 2, 0, minus 2, minus 4. So here you have whatever you want that is compatible with the Jordan here. So I'm not going to be more explicit, but let me stop it here. Okay. So these guys, they belong, of course, to SL. Here I have 5 elements, so I have 5, and then I put some more. So I don't know, whatever, delta, okay? And so these 2 vector fields, they belong to this Lie algebra, which is, I'm identifying which H naught of T Pn. And what happens is that they do the job. Okay, so you take the infinitesimal action here, and you throw in this, guys, and then could sing of this guy here, so let me call it H. Okay. So in case you're wondering how the cat came out of the bag, or the rabbit came out of the hat, this is just a Jordan form, and this is the associated SL2 triple. So I'm promoting this thing to an SL2 triple. So this is going to get a little more evident in what follows. So another class of examples, which I quite like, is that I take G, simple group over K, and I put characteristic 0. Okay? So I take A as a Borel subgroup in G, and I take X to be the variety of Borel subgroups. Okay? So this is the variety whose points over the algebraically closed field K correspond to Borel subgroups of G. And and given X inside of the Lie algebra, so of course G is acting here on the left. Okay, so I kill the action on the right, and I have G acting on the left. And if I take X in the Lie algebra, then I can consider this this space X of X, which is family of Borel. So B is a Borel subgroup of G. So this is the variety of Borel subgroups, such that X belongs to Lie of B. Okay. So this is what people call the Springer fiber, because when you resolve the singularities of the nilpotent cone, these guys are the fibers. So when there is only one, it means that your fiber is regular. So the singularity of the nilpotent cone is not there. Okay? So these guys have been very, very much studied in the past 50 years by group theorists, so Springer, Steinberg, all these guys. And this is just the set of singularities of this vector field. So X is an element of the Lie algebra, so it's a vector field here, and this guy is just the singularities of this vector field. And all I have to do is to quote the work of these guys, and I get almost everything for free. So I have my theorem, which is a beautiful theorem, which says that dimension of X equals the rank of the group plus the dimension of the center. And of course, the formula cannot be so easy, so it's too beautiful, but there's a factor of 2 here to make it a true statement. But so you see that the dimension of this guy is just, at the end of the day, is just a centralizer of this. And now I can easily find vector fields or algebras of vector fields which have a very small singularity set. So I'll give you the upshot. Theorem. So I said G is simple. So G is not of the small Lie type. Okay, so I throw out some linking diagrams. A1, A2, A3. So then B2, C3, G2. Okay, so I throw out these guys, and then I get for free. Singularities of the distribution given by this Lie algebra, Kodim. Okay. So this means that in order to apply the theorem, I only have to use the. So why do I have to throw it out here? Because I need to compute centralizers. Okay. So at the end, I need centralizers to be small. Okay. So I split into unipotent and nilpotent, and you do some Lie theory, and then you bound the size of the centralizer, then you bound the size of the singularities of this thing, and then you bound everything, and you get this. Okay? So this result works as well. If you want the dimension 50 something, and you still want a bigger or equal to 3, then you just have to throw out more and more Lie types. Okay? But then it works. Okay. So that said, so I move on to the foliation. So I'm doing foliations of dimension 2. So I put a 2 down here. And I explain to you how do I get components of that.
This 2 means codimension 2?
No, downstairs is dimension. Downstairs is dimension, sorry. Yeah. Upstairs is codimension. Okay. So I have 2 cases at hand. I mean, 2 cases in which I can produce foliations which have small singularity sets. So I will look into G is SL n plus 1. Or G not of type so this is Borel case. So then once you have these guys, what you can do, so moral, it's a theorem, but maybe it's a boring theorem because, well, so there is some proposition, let's say. There exists a function psi from S Lie 2 of G into fol 2 of X with the twisted, so this is the determinant of the normal, so it's going to be Tx. So X here is just either Pn or one of these homogeneous spaces, okay? Such that. So this is using the theorem, once I have that, such that number of irreducible components of S Lie 2 is smaller equal number of irreducible components of fol 2. Okay. In the case Pn, this is a rational map. And in the case Borel, so this is for Pn. And in the case Borel, this is an actual map. Okay. So what is this theorem? So you take a Lie algebra, construct a foliation. I can assure that the codimension of the singular set is not too big. So I land in here. The theorem which I stated in the beginning allows me to say this is somewhat open. Okay? So this is an open set, this is an open map. So I will take irreducible components to irreducible components, so you push the number of irreducible components up. And then, just to end, probably the best part, is that everything here was done to be able to bound the number of irreducible components of this guy here. So what is S Lie? So this is the closed subscheme of the Grassmannian of dimension 2 and G, parametrizing subalgebras of dim2. Okay. So I'm here still in characteristic 0. Okay. Theorem. Irreducible components S Lie 2 are in bijection. Yeah, well, I'm somewhat assuming that G is simple also. It was semi-simple works, but thanks. Oops. Is orbits in the nilpotent part of the Lie algebra. Okay, and this correspondence is done as follows. So I take my H here, S Lie, and I'm going to associate something. So say at H is a billion. And then take orbit. If H is not a billion, then when I derive the algebra, I get into a nilpotent element. And because nilpotent elements, all the lines, if I take a nilpotent element and I look at the line which passes by this nilpotent element, this is all contained in a single orbit. If not, HH is nilpotent and non-zero and contained Yeah, yeah. G is acting on a joint. Yeah, so maybe. So G is acting on G himself. Okay. So this is the bijection, which gives you the number of irreducible components for this guy, and from that you take the corollary. Number of irreducible components of fall 2 Pn with degree in whatever. At least for n big enough, okay? So it's bigger than e to the, so what's the formula? And the same will be true for the Borel variety. But then, so at the end, you may wonder, where does this number come from? Is that because nilpotent orbits in SLN, they're just partitions, because you have the Jordan form. Okay, so the Jordan form takes care of all the nilpotent orbits, and you have to count partitions, and you find your favorite you find your favorite lower bound for the number of partitions, and then the other one is corollary in the Borel case. G is not of type A1, this list G2. Then instead of, then you start getting tired, and instead of looking for a really closed formula for the number of for nilpotent classes, you just say that it tends to infinity. And G of type A, AR, BR, CR, DR, then number of irreducible components of fall 2 of the Borel variety, so G mod A tends to infinity with R. And well, it's 11:50, and I don't think I have any more else to say. Thank you.
Questions?
Sorry, I got a bit confused. What is the role of the integrability condition? So when you stated your theorem, you stated for foliations, but then it seems that it was just as distributions, and here you got foliations again, so you just check it separately.
Yeah, because there's no need for integrability in the theorem. Of course, there is then another part of the theorem which is to deal with the Kupka case, which takes care of integrability, but then I just left it out completely.
Thank you.
But yeah, you don't need it for anything here.
So in your first theorem, where do you really use the Noetherian assumption?
In the proof, you need
in the first theorem.
Yeah. Because in the first theorem, so I mean, the first theorem has a long proof, and it's, if you want to prove in this generality, then what you do, you pass to DVRs. So you check the theorem on a DVR. And if you want to do that, then you have to be Noetherian to specialize.
But there is no the standard trick of reduction to the.
Oh, yeah. Well, probably, yeah. If you want to do EG
Okay.
8, 4, 8, yeah.
And then in
I
the-
didn't touch that.
In the last part, is there any point, instead of looking at the Borels, looking at the parabolics? Do you get anything interesting or different?
This is an excellent question, and I need a representation theorist because I'm unable to find, the correct Steinberg formula for parabolics. So Steinberg doesn't prove it. Mm-hmm. And in fact, Steinberg always works with unipotent elements. And then in order for you to work with the Lie algebras, you already need to be guaranteed by someone who really knows what he's doing. So it's like, that's McGovern. So he explains the theorem, it's true. And then if you want to push it further, then you either understand very well the Steinberg theory or you don't touch it. So maybe, yeah, that's a question for the future. Yeah.
Thank you.
Any further question?
Thank you for your talk. I was wondering if your main result about openness could be applied for sheaves of Lie algebras.
At the end of the day, the theorem itself, I didn't state it like that, but the theorem is a theorem about sheaves. So it says something roughly like that. If you have a sheaf which is reflexive, and when you restrict to some fiber and you take double jewel, and this guy is not very singular, so it means that it has singularities of some bounded codimension tree, then the sheaf itself, it's locally free. So it's quite a general result, but it's commutative algebra and SGA too. Yeah, that's it.
Thank you.
No problem.
Any further question? Okay, we thank you very much.
Thank you.